Swayam Prabha. Digital India. Educated India.
Okay, so last class we saw this cache. This is for the multiprocessor cache, and so each cache line has a state. We had only one state in our earlier uniprocessor cache, but we have 2 bits, meaning 1 bit for the state. Now we have 2 bits, and we need 2 bits because we need to have we need to maintain 3 states. It's just not invalid and valid, but it is invalid, shared and exclusive. And the state of a cache line will change because its own processor does something, which is this larger state machine that you see here, this machine that you see, while it can also be changed because of some activity on the bus, which is shown by this smaller machine. Okay, so there is a simplest of the protocol is a token ring protocol, wherein there is a common shared bus and each processor gets the token. There is one token that is rotating. When I have the token, as a processor I become the master of the bus and I can do read and write on the memory, and that is what happens because of that read and write to my own cache is given on the right hand side, the larger one. And when I do not have the bus, I do not have the token, I am not the master of the bus, at that point of time I will be snooping on what is happening, and that is given by the left state machine. Okay, and when something is happening here, that is on the larger state machine, when something is happening because of my CPU, I keep broadcasting some messages on the bus so that I can basically take care of the cache coherency issue, right? Did you all get this? So this is what we saw in the last class, and now we will do an example and then go into the what we call as the parallel models of computation. Okay, so okay, so this is the model of our system. We have processors. Each processor has its own individual register. There are caches, and we are following a write back policy, and there is the memory is connected to the common bus, and that bus we call a Snoopy bus because it allows you to snoop. And now this is one state machine, the larger state machine. This is the state machine for CPU request. That is the Snoopy cache state machine 1. This is something because of my processor. This is what happens to a state of a particular cache line based on its own processor trying to read or write from the memory, and this is the smaller state machine. So whatever I explained is there in these 2 slides. Okay, now let us start doing this. Okay, so this is one example. We have 2 addresses A1 and A2. A1 and A2 map onto the same location, and let us say it is a directly mapped cache. So either A1 will stay or A2 will stay. Now this A1 and A2 are shared by say 2 processes, P1 and P2, right? Now these are all the actions that P1 does. P1 writes the value 10 to A1, as you see on the leftmost side. P1 writes the value 10 to A1, then P1 reads A1, then P2 reads A1. At the same time P2 writes 20 to A1, P2 writes 40 to A2, right? Now P1 and P2 are 2 cores and they have their own L1 cache. This A1 and A2 are addresses in the memory which will map onto the same location in that cache. So, and let us assume for our example that it is a directly mapped cache. So either A1 can stay or A2 can stay. Now what will happen? So this is one small case study that we will do to just re-explain that state machine. I hope you have understood what the state machine is. So initially the caches are all invalid. So the line in which A1 or A2 is getting stored in both the caches, both the L1 caches, they are in invalid state. So the state of, so we start off here. So what happens? So first one, P1 writes, okay, P1 writes the value A1 to 10. So in the P1's cache, A1 will be stored and it will have exclusive, right? So from invalid, when there is a write miss, it goes to exclusive state. This particular link, please note here, this link is exercised. So the value of A1 in the memory and the value of A1 in the L1 cache of P1 are different. So right, so I have written the value 10, it can be anything there, probably they can be different. Okay, so I have A1 as an exclusive address, so P1 has A1 as an exclusive address in its own cache, right, and this is this particular line. Please see the bottom state machine, I have marked it green, so this is that particular line getting announced. Are you able to follow, right? Now, so what will happen on the bus, I will say there is a write miss on A1, I need to tell, because there could be somebody who is having the value of A1 in exclusive or shared state, and now I have to say that now I am the exclusive owner of A1. So I will, on the bus, I will announce that there is a write miss. Who will announce? P1 will announce that there is a write miss of address A1. Nothing actually happens to memory. Okay? So memory, the value of A1 would be something, some junk, we don't know, right? Are you able to follow this particular step? Any doubts? Next. Now P1 reads from A1. When P1 reads from A1, it is already in exclusive state. It need not tell anyone, right, it is reading, okay. It just reads, it is just a read hit. Nothing happens on the bus. Please note that this is very, very important. Nothing happens on the bus. Bus is empty. Because I am just reading A1 and this is that loop here. This is a read hit on that loop here. So here itself there was a read hit. When there is a read hit, I need not tell anyone, because nobody is going to benefit by knowing that I am reading A1, because I am holding A1 in the exclusive state. Okay. Are you able to follow? Yes? Yes or no? Okay. So why should I not keep on broadcasting on A1 on the bus? If I keep broadcasting on the bus, then there is going to be more power consumption, right? When I send something on the bus, everybody will snoop, every cache controller will see what is happening, and there will be some energy spent there, there will be some power consumption there. So more I optimize on sending messages on the bus, please understand, the more that I am going to basically benefit in terms of power consumption, right. So in this case there is no necessity for me to tell, if I am holding A1 in exclusive mode by this state machine, there is no necessity, and if there is a read hit for that A1 itself, there is no necessity for me to go and tell everybody else, hey, I am reading A1. Normally today when you take the modern architecture, in this type of token architecture, there will be 8 cores, up to 8 cores they have scaled, okay. So the remaining 7 cores, if I just put something on the bus, the remaining 7 cores will start processing. What they should do, they will take that address A1, then they will say whether it is stored there, and if the valid bit is there, so they have to do all these checks. So when they see something on the bus, it essentially means they are going to access the cache to see whether that address is stored there, correct, right. So unnecessarily if I send a message, then some other 7 fellows will do a cache access. It is not that this cache controller is snooping that value. It takes that value, then go to the cache and ask, hey, is there something related to this? If there is something related to this, then it has to take action. If I am storing the address A1 and something is happening to address A1, then I have to go and check what should I do with that. So that means the moment some message is going on the bus, my cache gets accessed. Please understand the most important thing. So this is where we start gaining on the power. See, why suddenly we have what do you mean by optimizing on power? These are all the small things, right? These are all small intuitive steps that we need to take care so that we optimize on power. Okay, now let us see what is the third step. I will go to the next step. Okay. Now P2 tries to read A1. When P2 tries to read A1, what will happen? So let us be very careful, let us note it here. It first finds a read miss for A1. Read miss, it is trying to read A1, it is in the invalid state, so it puts on the bus that I am having a read miss. and I am trying to write A1. Correct? Now what will happen? Your fellow immediately on the bus P1 will say, hey stop, I have A1 in exclusive state, wait. So it will write back A1, it will write back the value 10 onto the memory. So on the address A1 10 will be loaded. Please note here, P2 now wants to read A1, P1 is having it in an exclusive state, right. Immediately what will happen? P2 says that there is a read miss on the bus, correct. That by the state machine we have seen, right, from the invalid state when I have a read miss I will say I have a read miss on the bus. Immediately P1 will be snooping because P2 is the master, right, P2 is reading, right, when P2 wants to read P2 will be the master, right. So P1 will be what? He will be snooping and now he finds A1. Now he finds A1 in exclusive state in his own cache. So immediately it will say wait, write back what? The value 10 into A1. So when it write back immediately in the memory you will see that A1 gets the value 10. Then what will happen? And then at the same time P1 will also make its state as shared state, please note here, because some P2 will also have the value of A1. Then what will happen? P2 will read the data, okay, will read the data from memory, P2 will read the data and it will also make it to shared state, okay. Are you able to follow this, right? So now when P1 had the address A1 as an exclusive address, when P2 wanted to read, P1 stopped that read, meaning not stopped, suspended that read, it wrote back the latest value of 10 into A1, then it made itself, it made its state as shared and P1 also, P2 also gets it in a shared state, right. This is how the cache coherency problem is solved. Is it okay? Now what happens? The next step, P2 write 40 to A2, okay, is the next state, okay. Okay, what will happen when P2 writes 40 to A2? Okay, P2 writes 40 to A2, what will happen? 1 minute, sorry, I think this should be removed. Yeah, now P2 writes 20 to A1, forget this for a minute, forget this for a minute, P2 writes 20 to A1, now what will happen? Now P2 actually should hold A1 in exclusive state. Now A1 is in which state? A1 is in shared state both in P1 and P2. So what will P2 do? When P2 writes 20 to A1, it will put a write miss on okay, oh sorry, it should put a write hit, sorry, it will put a write hit P2 A1 because A1 is there in the cache. So it will say I am writing into that cache, but that it will announce on the bus, okay. The moment it announces, and since it is writing, it will make P2 will make it as exclusive and A1 is the value 20, while P1 will be seeing the bus. Now it sees that P2 is writing into A1, it is holding A1 in shared state, so it will make that thing as invalid. Are you getting this? Yes or no? Are you getting this? Okay. So P2 now when it wants to write 20 into A1, P1 has A1 in shared state, it will make it invalid, while P2 will make its state as A1 state as exclusive. And then what happens? There is a write hit. It also tells on the bus when P2 wants to write 20 to A1, it will say I am writing something to A1, so that the other fellows will keep it. So this is from shared to exclusive. When I have a write hit, I say on the bus that there is a write hit, so that other fellows who are sharing can make it exclusive, okay. So the most important thing that we have to understand here is what is happening on the bus. Sometimes I announce on the bus, sometimes I don't announce on the bus. Why I announce, why I don't announce, this example is trying to make it clear. Right? Please note what would be the value of A1 in the main memory, it will still be 10 because this is a write back policy. Okay. Now in the next step I am writing 40 to A2. I am writing 40 to A2. Then what happens? There is a write miss on A2. Okay. There is a write miss on A2. Okay. So what will happen? But A1 and A2 are sharing a location, so I am trying to fetch A2, so I have to replace that A1. So what I do, I write back 20 back to A1 and then store A2 in the cache with value 40 with exclusive mode. Right? In the memory we do not know what is A2. The latest value of A2 is 40, which is in exclusive. The value of 20 is basically returned back into A1. Okay? Correct? Are you all able to follow what I am saying? Yeah.
Should be right hit, right? The first step.
Why did A1?
42 hit. This would be right hit. I think I changed it. Right.
In memory location.
First
A1
step.
mapped to the same thing.
P1 writes 10 to A1.
Oh, that's a right
Why
miss,
is
no?
that?
A1 was not there. No? A1 was not there initially. I am bringing A1, right? Initially both caches are invalid.
Is it compulsory?
Compulsory. Okay. This is right hit. Okay. This is right hit. Sorry. Yeah.
Sir, before P2 writes 20 to A1, if it writes 40 to A2,
No, it cannot. Because it is 20 is in the cache, right? From cache I should deposit in the memory and then only go and replace the cache.
so like first we should do write back.
First we should do write back and then write 40. Right? Now, did you all follow this example? So what we have done is, we have taken this state machine and we have basically, okay, we have taken the state machine and basically we have explained the different steps of the state machine. So, okay, before we go to the thing. So essentially this is the state machine and we want to verify each of these actions, right. Now what we have done is, by using those 4 or 5 cases, we have verified some of these edges, right. There are 1, 2, 3, 4, 5, 6, 7, 8, 9 edges. Every edge we should verify, right. So suppose you have coded this state machine in an hardware description language like hack, you did hack, right. So suppose we have coded this machine, we need to see whether it is working correctly or not. This is basically called functional verification. What we do, we give test cases to verify if it is working correctly. So what it means to verify a state machine? First thing is, we have to verify every edge. Then we may have to verify every path, from invalid shared to exclusive, invalid exclusive shared, invalid shared, shared exclusive, exclusive invalid. So different parts I can take. So this is called, one thing is called state coverage. State coverage means I visit every state, right, that we have done. So we have seen invalid, shared and exclusive on both the state machines, right. Then there is something called edge coverage. We have not done full edge coverage, but we have done almost, right. Every edge we need to cover once. Then there is path coverage. Every path we would like to cover, right. There are infinite number of paths. The moment I have a loop, then I could have infinite number of paths again and again, right. But I need to come out with some comprehensive coverage. So I need to see, one of the important aspects of computer architecture is, the moment I design a system, I need to test it, verify that system whether it is working according to the specification. So this is the specification, and you will write the code in some Verilog or BlueSpec or some language, okay, or any system Verilog, etc. And now we need to see that whether that implementation essentially meets this specification. So what are the different types of coverage? Again I repeat, state coverage, edge coverage, path coverage. We have done some part of it as the example. Okay. So there is one famous question, right? We are now talking of cache miss. If I don't find an address, then I call it as cache miss. If I don't find a page, I call it as page fault. Correct? Why can't I call it page miss and cache fault? Why should I say cache miss and page fault? Okay, think about this. Okay, why I say it's cache miss and that has page fault? Why can't I say page miss and then cache fault? So what is the difference between a fault and a miss? Okay, we will go to the, is it all fine? Did you all follow? So this is, there are n number of such cache coherency protocols. Right, you have a machine, you have a CPU for your mobile phone, you have a CPU for a desktop like this, and you have a CPU on a server class. What is the difference? They are the same instruction set, they run the same executable, but what would be the major difference? The difference would be, one of the major difference would be the cache organization, okay, right? And so what is the change in the cache? See, the way cache is organized is completely virtual to the compiler, completely virtual to the user, correct? So because cache, even if there is no cache, your program will work, but it will work slow. If I completely go and invalidate the cache and I remove the cache, I disable the cache, suppose I have a facility to do that, still your program will work. Every time it will come to memory and do that. But so everything depends upon the cache in terms of getting very good performance, especially in high end computing or high performance computing or whatever we call that. Okay, so right, cache architectures make or destroy a server. Now we will go to the last part of this course, which is very interesting part. Now we will now talk about parallel programming. Okay, so let me just okay, we will just talk about a bit of computing here, but then we will go and look at lot more on the programming. Okay, so what happens is, I'll cover whatever I am going to say now in a broad detail in my sort of last 2 lectures, right, where I am going to motivate you to what else is pending in computer architecture. I want to cover a bit of history of computer architecture before I wind up the course. Okay, so I would have started with that, that would be boring, so I am pushing it to the last and trying to keep it much more interesting, because you will start appreciating lot of things of why certain things happened after taking this course. You will start appreciating history after you understand current day computing, okay, and the challenges. Okay, so now what happened in say 2002 to 2005, the power consumed by a system is directly proportional to the frequency of operation. Okay, it is also proportional to the voltage of operation. Now as I keep increasing the frequency, my power consumption started increasing and it started hitting a wall. The wall, essentially the wall in this case is that chip started actually burning, okay, right. So I started, instead of having a constructive computing, I had a destructive computing, okay, and this was demonstrated in several places where you switch on the system, laptop actually burnt. There are photos of laptop actually getting burnt because of power issues. Okay, the interesting thing that happened here was that if I had a program that will run on a single core, and I take a 2004 machine, that will be faster than the 2010 machine, correct? Because if I had a program that will run only on a single core, in a 2004 machine it was running on a 3.5 gigahertz processor. Now in a 2010 machine it is running on a 1.2 gigahertz processor, correct? So what happened? the program used to run very fast in old day machine. Now it is, as I know, I am investing more money, but my program speed is getting low, right. That essentially forced people to go and start looking at multi-core programming, or what we call as parallel programming, right. When I want to do parallel programming, essentially that means that I have a task, I want to split it into small tasks. Instead of one fellow doing all the job, I will make two fellows do part of the job and I will take back the result, correct. So if I had 100 numbers, instead of one fellow performing 99 additions, if I have 4 fellows, each can perform 24 additions, and then one fellow can perform the 4 additions and give the answer. And what do you get here? I get the speed. Now I improve the speed 4 times, right. Instead of a one processor handling 99 addition, there are 4 processors concurrently handling each 24 additions, and then one more processor handling the remaining 3 additions. So I get immediately that speed up. But when I want to do this, right, one of the important thing is that if I have a task and I am splitting it into small tasks and giving to each one of the processors and asking all of them to do concurrently and giving me the answer, I now see the parallelism, I now see the speed up. But then these processors have to talk to each other, right. They have to sync their operation. I have split the task into 4 parts. It is not that all the 4 can work in isolation, okay. I have to stop at intermediate places and exchange information, and the way to we exchange this information essentially forms the building block of this whole thing, right. If I exchange the information through memory, then it becomes a shared memory architecture. But when I want to exchange the information, I need to basically have certain constructs by which I can do this in an effective manner, okay. Let me motivate this. Now we will look at things like I want to just talk about 2 things. I have to just talk about one aspect here which I call it as barrier, okay. Let me just talk about barrier, and then we will go to this parallel models, okay. Today I will talk about barrier, and then from tomorrow's class for next two classes I will basically cover the parallel models of computation, okay. Now let me explain barrier. One of the most famous parallel computing beneficiary is the field of what we call as finite element methods. You talk to aerospace, you talk to biotechnology, you talk to A, B, C, civil engineering, you talk to D what course is there? D, E, electrical engineering, okay. You talk to all these people, one thing that you will learn is that they all do some sort of a finite element method, especially mechanical, civil, aerospace, naval, ocean, material science, right. So what is this finite element method? See, let us take some simple problem, like, okay, now this is one floor, rooftop. On top of it I am keeping a generator, okay. This is a power generator. Now I am switching it on. Now this will start shaking. I want to see how that shake propagates through all these directions, right. When I stand here, I will have vibration, more vibration. As I go here, the vibration, so I can form circles, and as I go from the innermost circle to the outermost circle, my vibration will decrease, right. Now I want to study what will be the vibration here, here and all. So by this I could see whether the floor will fall down if I put the generator. I want to simulate it, right. So what I do is, this entire floor I split it into small grids. each square here is called an element. Okay. As I keep shrinking this grid size, more and more elements will come. Okay. But I am now essentially partitioning. There is a difference between division and partition. Okay. Discrete mathematics, did you learn? What is the difference between division and partition of a set? Set S is divided into D1 subsets D1, D2. Essentially means D1 intersection D2 need not be necessarily phi. But if D1 intersection D2 equal to phi, then it is partition. Okay. So that's the difference between the word partition and division. Now I am actually partitioning the entire thing into small elements, finite in number. That's why it's called finite element. Now what I do, now I have mathematical equation which can simulate a vibration here. I am doing it in blue color. It will simulate a vibration here, and which will tell you how much it is spreading to this. After that, from here this will spread to its nearest neighbors. Slowly I will keep seeing how this vibration spreads. So I analyze element after element over the every time frame t equal to 1, t equal to 2, t equal to 3, whatever the time units. Every time unit I will see what is the state of every element. A state of an element depends upon, is influenced by the state of its nearest neighbors and itself. Okay. So let there be a function f of a neighbor A is actually dependent upon some f dash of its own self A and its neighbors n1, n2. You have 1, 2, 3, 4, 5, 6, 7, 8, right? There are sorry 1, 2, 3, 4, 5, 6, 7, 8, n1, n2, n3 till n8. Right? So at time t equal to 1, I evaluate this. Then at time t equal to 2, again I evaluate. So every time what I do, I take myself, I take the values of my nearest neighbor, compute a function and put that value, and then again I will go do the next step. Right? More the number of, more finer is this grid, what will happen? My accuracy increases. And you already see that this is embarrassingly parallelizable, right? So what I can do is, I can split it into, what color here? Color. Okay, I can split it into 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 processors. So each one processor will be responsible for this, P2 will be responsible, P3, P4, P5, P6, P7, P8, P9, P10, P11, P12. So everybody will start computing, right? But please note that at the end of one time step, everybody has to wait for everybody else, because this end border point, right, when I want to compute for t equal to 2, it needs the t equal to 1 value of the edge. So let us say we 8 are computing this. When I finish my part, I have to wait for you to finish the other part so that I can get the latest value. So every processor is working independently, but when I finish that part, I have to basically wait for all of you to finish and then I can go to the next part. This is basically called as barrier. So I put a barrier at the end of every iteration. What will happen? When everybody hits that barrier, then everybody will start. Okay. Now tell me, how can you implement barrier? Where have you seen something close to this in this course? Fine. So atomic instructions. What are atomic instructions? Instruction that cannot be stopped in the middle, right? So this is basically an atomic instruction. So we have seen test and set, swap, couple of instructions I have basically introduced, and we show that how the producer and consumer can sync by using this atomic instruction. I gave you a small algorithm I taught in this class, okay, right? So barrier can be basically implemented using atomic instructions, okay. So that is one very important thing. So before we wind up today. So this is how barrier works. There are 3 processors. I put one barrier here. Okay. So when this is a barrier I put in all the 3 programs. When somebody comes to a barrier, he will stop. This fellow is coming to the barrier, he will stop. This fellow also comes. When all the 3 fellows reach the barrier, all the 3 will move out. Okay. And the way you implement the barrier basically synchronizes processors by blocking until all of the participating processors have called the barrier routine, and there is actually no exchange of data. So barrier is one particular construct that we need to build when many processes are working on that. Okay. Right. With this as an basic building block, I will now go and start teaching you the PRAM, which is the parallel random access memory. It is very important. I will give you some clues of how to go about programming multiprocessor architecture. Okay.